Ever wondered how the atom, the basic building block of matter, was first imagined to look like? Let's rewind to the early 20th century. Enter Ernest Rutherford, a physicist who envisioned the atom much like a mini solar system. In his model, the atom had a dense, positively charged center known as the nucleus, around which negatively charged electrons orbited, much like planets around the sun. This concept was revolutionary, and it was backed by Rutherford's groundbreaking gold foil experiment. However, this atomic model wasn't without its flaws. It couldn't explain why atoms were stable and didn't just collapse due to the attraction between the positive nucleus and negative electrons. Moreover, it failed to account for the observed spectrum of hydrogen and other elements. While Rutherford's model was a breakthrough, it still left some questions unanswered. So, how did we move forward from Rutherford's model? Enter Niels Bohr, the physicist who proposed a new atomic model. Bohr's model addressed some of the shortcomings of Rutherford's model, primarily the issue of electron stability. In Bohr's model, electrons move in fixed orbits around the nucleus, each orbit corresponding to a specific energy level, often referred to as shells. This model successfully explained why electrons don't spiral into the nucleus, and also gave us an understanding of atomic emission and absorption spectra, a phenomenon where atoms absorb or emit light at specific frequencies. But, as with any scientific model, Bohr's model had its limitations too. For instance, it worked well for single electron atoms like hydrogen, but failed to accurately explain the spectrum of multi-electron atoms. So, while Bohr's model was a leap forward from Rutherford's, it was not the end of our atomic journey. Bohr's model was another step forward, but still, it couldn't explain everything about the atom. But then, how do we explain the behavior of electrons in multi-electron atoms? Well, we introduced the concept of shells and subshells. Picture an atom, not as a mini solar system, but as a bustling city. The city center or nucleus houses the protons and neutrons. Surrounding this are different neighborhoods or shells where electrons reside. These shells are further divided into subshells, each with a distinct energy level. Like apartments within a neighborhood, subshells accommodate various numbers of electrons. The first shell has one subshell, the second shell has two, and so on. As electrons fill these subshells, they give rise to different atomic properties. For instance, the arrangement of electrons in the outermost shell determines an atom's reactivity. Understanding shells and subshells is like decoding the city's layout. It helps us predict the behaviors and interactions of atoms, the building blocks of our universe. Shells and subshells give us a better understanding of the atom's structure, but there's more to the story. But did you know both matter and light have a dual nature? Yes, they do. This concept, known as wave-particle duality, is a fundamental principle in quantum physics. It tells us that every particle can also behave like a wave, and every wave can behave like a particle. Let's take light, for example. Sometimes, light behaves like a stream of particles, which we call photons. This particle nature of light can explain why objects cast shadows or why light can cause certain materials to emit electrons, a phenomenon known as the photoelectric effect. On the other hand, light can also behave like a wave, spreading out and interfering with itself. This wave nature of light can explain phenomena like diffraction and interference patterns. Similarly, matter, which we typically think of as particles, can also exhibit wave-like behaviors. This is most evident in the microscopic world of atoms and subatomic particles. This dual nature leads us to a fascinating concept, the de Broglie relationship. Now, what happens when we combine the wave nature of matter with its particle nature? This is where de Broglie's relationship comes in. It's a remarkable concept that links the two aspects of matter. De Broglie proposed that particles of matter, not just light, also exhibit wave-like behavior. This was a revolutionary idea because it suggested that all matter has a dual wave-particle nature, not just light. So how does this work? Well, de Broglie suggested that the wavelength of the wave associated with a particle is inversely proportional to its momentum. This relationship is used in modern physics to predict the behavior of particles at the quantum level. The de Broglie relationship has profound implications. It means that we cannot predict with certainty where a particle will be at a given time. This uncertainty is a fundamental part of our understanding of the physical world. The de Broglie relationship is just one of the many fascinating concepts that have come from our quest to understand the atom.